GLEX Global Exploration.
Okay, thank you everyone for attending this session to learn about the James Webb Space Telescope. Now, traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do, and this is a major use of space telescopes. Looking back in time is made possible by the finite speed of light. If you look at the person seated next to you right now, you're not seeing them as they really are. You're seeing them as they were a few nanoseconds ago. Why? Because that's how long it takes light to travel 1 meter. Now, a nanosecond is a really, really small amount of time. So that transmission delay is imperceptible to us. But if we look at objects farther away, the effect becomes more pronounced. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen, because that's how long it takes light to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. If we look at the nearest star, we see it as it was 4 years ago. The center of our galaxy, we see it as it was 25,000 years ago, and so forth. And so with telescopes, we can look back in time to observe the evolution of the universe. Now, the Webb mission was conceived in the early 1990s to connect the dots, if you will, between the famous image shown at the upper left, an image of the oldest light in the universe, obtained with NASA's COBE satellite. A Nobel Prize was awarded for that image. Now, the pink and blue blobs in that image denote temperature inhomogeneities, which are the seeds from which galaxies will eventually form. Now, about this time, the Hubble Space Telescope was launched, and the Hubble telescope took the deepest image that it was capable of taking, which is shown at the lower left. And that image shows us what the universe was like when it was about 1 billion years old. The COBE image shows us what the universe was like the moment it became transparent. And between those two epochs shown on this cartoon is a mysterious, poorly studied epoch known as the cosmic dark zone. And this epoch is of tremendous scientific importance because it is the period in the evolution of the universe when the first stars and galaxies formed. And it's poorly studied because we have never had the right type of telescope in space to study it. Now, you've all heard the statement that space is expanding. What do we mean by that? This analogy tries to explain that. Here we have a loaf of raisin bread dough that's been put out to rise. Imagine you are seated on one of the raisins. What would you see? You would see all the other raisins moving away from you. And no matter what raisin you chose to sit on, you would see exactly the same thing. Everything would be moving away from you, even though you are not at the center of the expansion. That's a pretty good analogy for what we mean by space is expanding. Well, what does this have to do with the James Webb Space Telescope? Well, in order to see the first galaxies in the cosmic dark zone, those galaxies emit their light in the ultraviolet. But as that light travels to us through the expanding space, through the expanding raisin bread dough, its wavelength is stretched into the infrared. So to see that light today, we have to build an infrared telescope. And the infrared capability that we put into the Webb enables it to pursue lots and lots of other science that we'll talk about. So what is light? Light comes to us. Light exists in an infinite spectrum of wavelengths, from infinitely short to infinitely long. And only a small slice of that spectrum can penetrate the atmosphere to reach the surface of the Earth. So our eyes have evolved to be sensitive to that small slice. But there's way more light out there that our eyes cannot see. The Hubble Space Telescope was designed to operate in the visible part of the spectrum and the ultraviolet part of the spectrum. Our eyes are not sensitive to ultraviolet light, but our skin could be burned by it if you stay at the beach too long. In contrast to that, the Webb telescope was designed to operate from the red end of the visible out into the infrared. Our eyes cannot sense infrared light, but your skin can sense it. If you hold your hand near a warm radiator or a warm stove burner and you feel the heat, what's happening there is your skin is sensing the infrared light. Now, everything we know about the universe is transmitted to us in starlight. And much of what modern astronomers do is extract physics information from the starlight. And so in order to learn about the universe, we want all the light. To get all the light, we need to put our telescopes in space. So this is a major reason why we put telescopes in space. And in the Webb mission, we're focusing on infrared light, which is, heat radiation. All right. Now, the spaces between the stars in our galaxy, the so-called interstellar space, it's not a cold, empty vacuum. It's filled with giant clouds of molecular gas and dust. Now, when the Hubble Space Telescope, early in its mission, Hubble imaged a portion of this object called the Eagle Nebula and took this very famous image. It's been called Pillars of Creation. What you see here are filaments of a giant molecular cloud. So this is a big cloud of gas that consists of molecular hydrogen, and it's mixed with lots and lots of dust. And the dust makes the filaments opaque. Now, we'd like to see into those filaments because inside those filaments, stars are being formed. And when we observe this same field with the infrared telescope, the longer wavelength infrared light can penetrate the dust so that we can see the star-forming action inside with more clarity. Here's another example from the Webb where we have image of one of these giant molecular clouds. And with the infrared capability, we can see stars forming in these clouds. We can see ultraviolet light from newly formed stars are impinging on this cloud, breaking up the molecular hydrogen. You can see the hydrogen streaming back into space. We see objects that are still embedded in the stars, in the cloud, and objects that are emerging, denoted by their diffraction spikes. With JWST's ability to see fine detail and its infrared ability, we can study star formation in our galaxy like never before. Now, we know the basics of star formation, how stars form. Stars form when these giant molecular clouds collapse onto themselves by self-gravity. When the clouds collapse onto themselves, the pressure in the center of the cloud begins to rise. And as the pressure begins to rise, the temperature begins to rise. It's much like when you fill your bicycle tire at the gas station, the tire gets a little bit warm when it's fully compressed. Same thing happens in the cores of these giant molecular clouds, but here the temperature gets really, really, really warm to the point where nuclear fusion can occur, and then the star is born. And it's shown on the right end of the top panel there. When a star is born, it's typically surrounded by a circumstellar disk of material. You can think of this as material left over from the star formation. And these circumstellar disks are of tremendous scientific interest because they are the birthplaces of planetary systems like our own. And when planets form in these disks, as the planets orbit the star, they sweep up material from the disk to cause the disk to take on this sculpted appearance as shown in that simulation. And here you see radio telescope imagery of sculpted circumstellar disks. And so one can see that we can infer the presence of planets in these circumstellar disks without even having to see the planets themselves. Here is a very recent image of one circumstellar disk from the star Fomalhaut. Here you see Hubble's image. Hubble can show this outer ring. The big black thing in the middle of the Hubble image is a coronagraph that is blocking out the light from the star. When JWST observes this disk at a much longer wavelength of about 24 microns, the star is dimmer, so we don't need the coronagraph, and we can see the inner structure of this disk for the first time. All right, now at the upper left, you have an artist's rendition of the debris disk around our star, the sun, alongside a map of where that debris actually is. These are the so-called Kuiper Belt objects. These are chunks of rock and ice left over from the formation of our solar system. So they're of great scientific interest, and we want to study those. And we've put special non-sidereal tracking capability into the Webb to allow us to observe this debris and the outer planets of our solar system. Now, a few years ago, 2014, we got our very first image of a Kuiper Belt object. NASA had launched the New Horizons mission, which was a flyby mission to Pluto. And when it finished the Pluto part of its mission, we sent it on to observe this Kuiper Belt object. And this is what we saw. It turned out to be two objects fused together. And subsequent computer analysis has shown that objects like this can fuse as a result of a very low velocity collision, a few meters per second, without either object being destroyed in the process. And this is of great interest for theories of planet formation, in which planets form by successive agglomeration of smaller particles into larger bodies, eventually forming a planet in 10 to the 8 years or so. The Webb will do a lot of work on the Kuiper Belt objects. Now, some of the most interesting work that the Webb will do in the outer solar system is on moons of Jupiter and Saturn. These moons are of great interest because they're believed to be ocean worlds, worlds that contain vast oceans covered by a thick crust of ice. Tidal forces act on that ice, causing it to crack, and material erupts through those cracks, creating a geyser-like phenomena, shown here in this image from the Cassini spacecraft on Enceladus, a moon of Saturn. This is of interest for the search for life in our solar system. As you may know, studies of the mid-Atlantic ridge have revealed rich life that is completely disconnected from the sun, living on thermal energy from these volcanic vents. The same thing could be happening in these oceans. And so the Webb is studying the ejecta from Enceladus to understand what it consists of and understand its relevance to life. And this is a very exciting result that we've got on Enceladus. We've seen that water has erupted to such an extent that there is this giant ring of water vapor that is being left in Enceladus's wake, as one might say. And we've obtained a spectra of that, and we're able to understand its chemical composition. Understanding is in progress. This is Webb's first image of Jupiter. It's stunning. One can see that our non-sidereal tracking is working very well. We see tremendous clarity here. One of the interesting things in this image is that one can see aurora forming on the poles of Jupiter. This is the same type of phenomena that occurs on the Earth, producing the northern lights. Here you see Jupiter's great red spot. This is a storm that's been raging on the surface of Jupiter for 400 years. Today we see the red spot is shrinking. The Webb may help us understand why it's shrinking and why the red spot is red. We still don't know why the red spot is red. The Webb has shown us rings of Jupiter and very small moons of Jupiter. This is the Webb's first image of Uranus, and it shows the rings of Uranus like we've never seen them before. These rings are particles of ice and rock, and the Webb, with its infrared capability, is exquisitely sensitive to ice and rock, and so we can see this kind of detail. Now, when I was a graduate student, there were no planets known outside our solar system. Today, we've identified more than 5,000, with the implication that there must be tens of billions of habitable worlds in our galaxy. We don't know that they're inhabited, but we have learned how to search for life on them by studying the composition of their atmospheres. So the search for extraterrestrial life is no longer the stuff of science fiction. It is very much a major science objective of NASA, and the Webb is really starting this process in great detail. So how can we search for life on an exoplanet that we can barely see? We use a process called spectroscopy, in which we can spread light out into its component colors with special optics to allow us to see the emission and absorption of light by individual atoms and molecules in the atmosphere. And we can actually tell which atom and molecule is producing the emission and absorption that we see. So in this example, we show the spectrum of the Earth, Mars, and Venus. So what is this spectrum? It's a plot with brightness on the y-axis, wavelength on the x-axis. And all, in the case of the spectrum of the Earth, all these bumps and wiggles are produced by emission and absorption of individual atoms and molecules in the atmosphere. If Earth had no atmosphere, this spectrum would be just a flat line. What we're looking for is chemical species that would be indicative of life, so-called bioindicators or biomarkers. And the Webb will enable us to do this on planets that are somewhat larger than the Earth. The Webb can detect water vapor on a planet that is a few times the size of the Earth. If we're looking for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather, in order to have life exist on a planetary scale, in order for organic chemistry to exist on a planetary scale, one has to have a liquid solvent available on a planetary scale, and water is what we're most familiar with. So we'll be looking for biomarkers. To make a case for life, we will have to detect lots of biomarkers over a broad spectrum, probably requiring multi-missions. But Webb is getting started on a wide range of candidate objects. Now, so here is some of Webb's first spectra on exoplanet atmospheres. The first things that you could see is that these are not a flat line. So these planets do have atmospheres. And we have been able to detect a lot of stuff. Sodium, we've detected water, carbon monoxide, and we've even seen sulfur dioxide, which is very interesting because sulfur dioxide is produced by photochemistry in the planet's atmosphere. So we're just getting started here, but with the Webb mission, we're going to learn a lot about exoplanet atmospheres, their spectra, their chemistry, and it should be fascinating. Okay, when we first put pencil to paper or marker to whiteboard on what kind of observatory we had to build to do that sort of science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope. And we needed Hubble's ability to see fine detail, angular resolution as they call it, in the infrared spectrum. And we needed an observing capability that spanned the optical to the infrared. When we realized those 3 things, we then realized that we had 2 enormous problems that almost stopped the project dead in its tracks. To get 7 times the light gathering capacity of the Hubble Space Telescope, we needed a mirror that was bigger in diameter than the biggest rocket. That was problem number 1. Problem number 2, to build an infrared telescope, the telescope has to be made very cold. Why? Everything above absolute zero emits light, and warm objects emit infrared light. So if you had infrared goggles on right now, you would see your body glowing, the walls and floor of the room would be glowing. If we didn't make the Webb very, very cold, it would be blinded by its own infrared emission. And then and now, there is no mechanical refrigerator powerful enough to cool something as big as the Webb, to the required temperature, which is a very low temperature, almost minus 400 Fahrenheit, or 40 or 50 degrees above absolute zero. So those were the problems that we had to solve right out of the box. Let's take a look at how we solved them. Let's talk about the thermal problem first. We didn't put the Webb in orbit about the Earth the way the Hubble Space Telescope and most satellites are. We sent it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And it's about 1 million miles away from Earth in the anti-sun direction. All right, how does this help us cool the Webb telescope? Well, in this position, as the Earth orbits the sun, this pattern of Lagrange points, of course, orbits with it. And so when an object is placed at the L2 point, the sources of heat on that object, the sun, the Earth, and the moon, will always lie in the same direction. So we said, okay, we'll deploy a giant sun shield so that the telescope can always live in the shadow of the sun shield. And then we determined that if it's in the shadow of the sun shield, it will cool to the desired temperature just by passively radiating its energy away to the cold darkness of space. And so that is how we cooled the Webb. We also have to be able to point the Webb all around the sky, or it won't be useful as a telescope, and it always has to stay in the shadow of its sun shield. So we designed the sun shield to be large enough so that we could tilt the telescope over an arc of about 5 degrees toward the sun and 45 degrees away from the sun, and it will always be in the shadow. And then you can see that if we rotate the Webb about the Earth-Sun line, about this line, that doesn't spoil our shadow situation at all. So now this arc turns into an annulus. That annulus covers about 35% of the sky. So at any instant in time, the Webb can observe 35% of the sky and still remain in the shadow of its sun shield. Now you can see as the Webb orbits the sun, so now we're rotating about this axis, this annulus will sweep over the whole sky every 6 months. So every 6 months, JWST can observe any spot on the sky and still remain in the shadow of its sun shield. Now, we didn't put the JWST exactly at the L2 point. We put it in a small orbit about the L2 point. Why did we do that? We're generating electricity with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so it was critically important that we stay outside of the Earth's shadow. All right. That sunshade was the riskiest part of the whole mission. You know, people often ask me, what were you worried about when you were watching the launch and thinking about the deployment? Almost everybody on the project was worried about this sun shield. The development of the sun shield was a remarkable achievement. It is literally the size of a tennis court, 70 by 40 feet. It has 5 layers that give it an SPF of 1 million. If you had this thing on the beach, it would be very well protected. Each layer is made of a heat-resistant plastic-like material called Kapton. Each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it really looks pink in reality, and the rest of the surfaces of all the layers are coated with aluminum. The layers are not flat. They have a special curved shape that's critical to getting the SPF of 1 million. Those of you who sew realize that you cannot make something curved out of flat cloth without lots of seams. And each of these 5 layers is actually a quilt of 50 pieces involving 7,000 inches of seaming. Here it's not done with needle and thread, but rather with thermal spot welds. So building this thing was an enormous achievement, and then figuring out how to deploy it in space was even a bigger achievement, but we did get that done. All right, here's an example of some deployment testing on the sun shield. These plastic tables on the side are there for gravity offloading. They're not there in space. And these telescoping booms pull the sun shield out of a containment pallet in which it is folded up. You can see a person appearing in the center here, so you can get a sense of a size scale for this. And so this shows you just an example of some of the testing that we do. You can see the quilting. These Spreader bar assemblies around the periphery spread the 5 layers apart from each other after the initial deployment, and tension a cord that runs around the periphery of each layer. It's a very complicated deployment procedure, but we did get it done, and it did work perfectly for us. All right, what did we do about the big mirror? To deal with this requirement of a mirror that is bigger in diameter than the rocket, we adopted something called a segmented mirror architecture. So rather than build one big mirror, we built 18 hexagonal segments that are mechanized so that they could play together as if they were pieces of the same mirror. And that allowed us to fold the telescope up inside the fairing of the rocket that we used. The rocket we used was a French rocket called the Ariane 5. This is a 5-meter diameter fairing, and this shows how the Webb fits in that fairing. This is an end view, so you can see there's not a lot of leftover space in there. This rocket is not launched from Florida. It's launched from Kourou Launch Center in French Guiana, which is on the east coast of South America. The Webb payload was 6.5 metric tons, and the origami involved in unfolding this telescope involved 50 major deployments and 178 release mechanisms, every single one of which was a single point of failure for the whole mission. Despite that, NASA let us actually proceed with this. All right, now the Webb mirrors are not made of glass, the way most telescope mirrors are. They're made of a metal called beryllium. Why did we choose beryllium? In order for the shape of the mirror to remain constant as the Webb slews to different positions around the sky, we had to find a material that would not expand and contract very much around a mean temperature of about 50 Kelvin. And it turns out that beryllium has that property. The beryllium starts out in a powder form. We have to compress it under tremendous heat and pressure to form what's called a billet of material. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is the back side of a flight mirror. This is the front side. You see laboratory equipment reflected in the mirror. And you can see that we've light-weighted the mirror, as we say, to an extreme degree. The Webb mirrors are about 6 times lighter than the Hubble mirror, which was the prior state of art. And this was critical to making the Webb possible, because when one is designing anything that flies, whether it's an aircraft or a spacecraft, mass is a tremendous premium. And so developing these low mass mirror segments was critical to the Webb. Now, we have another big problem. How do we polish telescope mirrors? We rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirror at room temperature and use it at 50 degrees above absolute zero, it means that we have to put the wrong shape in at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative procedure in polishing the Webb mirrors, in which we would polish them partway and then put them in a specially instrumented space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama, so that we can cool them to the operating temperature, observe them with special optics test equipment, and see how the actual results are tracking to our model. Then we would make corrections to the model and iterate this procedure. This took a long time. This is one of the reasons why it took so long to build the Webb, but it was completely successful. Now, when we finally got the Webb mirrors made, integrated with the structure of the telescope, and we got the science instruments made and got those integrated with the telescope, and we got the whole payload ready to fly, it was too big at that point to put into an aircraft. And so we put it on a roll-on, roll-off transport ship, and we shipped out of Seal Beach, California, just south of LA. We went through the Panama Canal over to Kourou Launch Center. The Webb was contained in this special mobile clean room, if you will, that keeps it preserved in the special atmosphere that it has to be in order to remain qualified for flight. All right, we're in Kourou Launch Center, and we're in the vertical assembly building. We're on an elevator, and we're riding up the side of the rocket. There are work platforms set up at various stages where people are working on the rocket, getting it ready to fly. We're going to go to the top to see the Webb being integrated to the payload adapter of the rocket. So this is the very last view of the Webb telescope on Earth. And you can see everyone's working in a super clean environment, which is why they're dressed the way they're dressed. And here we're integrating the fairing or nose cone of the rocket. And then the rocket is rolled out to the launch pad on a crawler vehicle. It actually moves much slower than that. You could walk alongside it. And then we got it out there, we launched it.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
All right, we got a great launch. Here are some first deployments. The solar arrays come out so we can become power positive. We're operating on batteries up to that point. You see the high gain antenna come out so that we could begin communicating with the Webb telescope. And this is what the unfolding of the telescope itself looks like. You saw the secondary mirror tripod unfold, and then the wings of the primary mirror unfold much like a round drop leaf kitchen table. All right, to get those mirrors to play together as one, each mirror segment is mechanized in 7 degrees of freedom, the 6 that you're familiar with, plus our radius of curvature. And so when we first launched the Webb and first looked at a star, we actually have 18 separate telescopes to deal with. And so the first pointing at a star produces 18 images. Then we would move each segment to figure out which image went with which segment. And then we superpose all the images onto each other to get an almost perfect image. And then we use special interferometric optics in one of our science instruments to get each segment to be coplanar with its neighbors to within a small fraction of the wavelength of light being observed. And that results in an essentially perfect image. The image quality achieved by Webb exceeds its requirements by a factor of 2. Now, it's literally true that the Webb is giving humanity its first high-definition view of the infrared universe. This is what we had in 2009. These are 3 images of the same spot on the sky. So these 4 stars are these 4 stars are these stars. With the WISE telescope, which ended its mission in 2011, this is our ability to see fine detail. With Spitzer's telescope, which ended its mission recently, this is what we could see, and this is what we have with the Webb. This is made possible by the size of the Webb's mirror. The bigger the mirror, the smaller the resolution element that can be achieved. So much of the Webb's science capability comes from this ability to see fine detail. Now, the Webb has observed the cosmic dark zone. We are seeing lots of galaxies, some of them more than 13 billion years old. We're able to take spectra of these galaxies and understand their chemical composition. We're very much looking for stars and galaxies that contain only hydrogen and helium because they will be the first generation that have not been enriched by supernova. This is an example of the death throes of a star like our sun. It's called a planetary nebula, has nothing to do with planets. When a star like our sun runs out of fuel, it will throw off its atmosphere into space to produce this nebula. And here we're seeing it in the near infrared. Here we're looking at hot gas and hot dust. And with Webb's mid-infrared instrument, we're able to see cold hydrocarbon emission and cold dust, and we can even see the progenitor star in its companion that gave rise to all of this. Here's an example, Webb's image of a supernova, Cassiopeia A. This supernova occurred during recorded history about 340 years ago. This is red stuff here is dust that is being produced by the supernova ejecta. So the ejecta is enriching the interstellar medium and material for subsequent generations of stars. And this green material here is from the original star. We see new phenomena with the Webb that we've never seen before. Episodic dust formation from this binary late type star, producing this remarkable pattern of dust bands. We've never seen anything like that before, and this is a Webb result. So the Webb is the things that we've learned from the Webb about the instrument itself right out of the box. The optical accuracy is about twice the requirement. Everything's working perfectly. We do have an unexpected vulnerability to rare, somewhat large micrometeorite hits, and so we have adjusted our operations to mitigate that. The early galaxies are bigger, brighter, bluer, and less irregular than we expected them to be. We haven't seen a truly primordial one yet. And the Webb has seen supernova, has discovered supernova, which is a little bit of a surprise because its field of view is very small. And we see a lot of gravitational lensing, and in those gravitational lensed images of the early universe, we can actually see individual star clusters, which is quite remarkable. And the data is of very high quality. So how does the universe work? How did we get here? Where are we going? And are we alone? Those are the central questions that drive NASA astrophysics. And the Webb mission is the next step in humanity's quest to answer those questions. And you can be part of that quest. The people that do projects like this come from all walks of life and all backgrounds. There's a quote that I'd like to read. "The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in a mathematical language, and its characters are geometrical figures." That's as true today as it was 400 years ago when Galileo said that. So to work in this field, young people, go to college, or if you're there, stay there, study whatever you love. But if that happens to include science, engineering, and math, then consider aerospace as a career option. If you want to know what it's like, you can apply for a NASA internship. We have internships for every level, from high school to senior faculty. And if you would like to join a NASA research team and work with real data, but you don't want to go through all the trouble to become a scientist, you can do that too. NASA has a rich citizen science program, and some of the images that you've seen from the Webb were actually processed by citizen scientists. What comes next? Only a few weeks, ESO will launch its Euclid mission, on which NASA is a partner. The Euclid mission will study dark matter and dark energy. Then the following year, the Vera Rubin Observatory will be commissioned. This is a giant ground-based telescope that will usher in a whole new kind of astronomy called time domain astronomy, where we're concerned primarily with the evolution of the night sky on very short timescales. Then in 2027, NASA will launch the Roman Space Telescope, which is a mission dedicated to understanding dark energy, and it will prove technology that will be needed for the Habitable Worlds Observer. This is the next big strategic mission that NASA will build and launch after the Roman telescope is launched, and this one is really designed to look at Earth-like exoplanets. Okay, those are remarks from now. They're telling me to get off the stage and a big hook will come out. So I'd love to answer questions, but you'll have to corral me afterwards. Thank you.